Welcome back, everybody. Today we're going to be talking about related rates. So the goal today is to learn how to use implicit differentiation to solve related rates problems. So far we've been looking at rate problems. That's what we've been doing in calculus. It doesn't always feel that way, but hopefully optimization made clear that derivatives are just about rates, and related rates here means that maybe you have more than one derivative, and those two derivatives, those two rates, are somehow related to one another. They have a relationship. Okay, so let's get into it. So the first problem that we're gonna do two problems. The first problem here is called the sliding ladder problem, or at least that's what I'm calling it. And here what you have is a ladder that's 5 meters long. So this is the ladder here. Excuse my bad drawing. And it says, say that the feet of the ladder, so this is the feet of the ladder, slips. So what's happening is this portion of the ladder is slipping. So if you want to imagine maybe the ladder in the future at some point, maybe it looks something like this, where this part of the ladder has slid towards the right, and this part of the ladder has slid down. Hopefully that picture is kind of clear. So what's happening is the feet are 3 meters from the wall and are moving at 10 meters per second. And what we want is at that instant in time, so at the instant in time when the feet are 3 meters from the wall and moving at 10 meters per second, we want to know what is the speed at which the top of the ladder is moving. Okay, so the idea is that as this ladder slips, the rate at which it slips to the right here, the feet slip to the right, is somehow related to the rate at which this top slips down. And what we want is how fast is the top slipping down at the exact moment when the feet are 3 meters from the wall. Okay, so that's kind of the problem. I think it's nice, the number one, with related rates problem, you need clear definitions. So let's define the variables that we're dealing with now. I'm going to call this the origin. We'll call this point A, call this point B. Okay, so A is the top of the ladder, B is the foot of the ladder, O is, let's say, the origin. I'm going to define two variables. Let's call X. Let's X be the length of the line segment OB. In IB math, we typically don't put a bar on top, okay? So it just, OB represents the length of the line segment, OB. I'll call this X. And then we'll also let Y be the length OA. Okay, so this is Y. Okay, so now we have a sense for the variables. These are indeed variables because, as you imagine, as the ladder slips down, X is going to increase. And as the ladder slips down, Y is going to decrease. And it's very important to understand how these things are changing. So the change in X is going to be positive. The change in Y is going to be negative. Okay. Okay. So the other thing I want you to keep in mind is that the rate at which X is increasing and Y is decreasing is somehow related. And that's why these are called related rate problems. Okay. So somehow their derivatives are connected. The other thing I want to make clear is that notice that here we have our rate in meters per second. And this is always going to be common for related rates problems, but the idea here is that all the rates are going to be expressed basically always in terms of time. And so what's happening here is at time t equals 0, maybe the ladder slips, and as x increases and y decreases, both of these are changing in relation to time. Okay, so I want to make a note of that, do it in a different color. I want us to note the following, that both x and y are implicitly functions of time. Okay, so x and y are functions of time. And this will basically always be the case with related rate problems. You have variables, but those variables themselves depend on some independent variable. In this case, let's say time is that independent variable. Okay, now the other thing that usually helps people is to make it clear what they're after, what they want, and this is similar to optimization. Let's make clear what we're looking for. So here it says, what is the speed at the top of the ladder, or what speed is the top of the ladder moving at this instant? Maybe I should make clear that the top of the ladder is moving down. Okay, so maybe we want to know how fast is the top of the ladder moving down? Okay, so really what we want then is how fast is this length y decreasing? Okay, so this is what we want. What we want is dy by dt. That's the rate at which the top of the ladder is decreasing or slipping. At least this dy by dt describes the rate at which the top of the ladder is moving down towards the ground. We want that. And what we want that at is when the feet of the ladder are 3 meters from the wall. So when x is equal to 3 meters. So we don't just want a rate, we want a rate at a particular instant in time, the instant in time when x is 3 meters. And that's going to be important. Okay, now here's a common mistake that people make. I don't want you to write this down, but a common mistake that people will say is when they're setting up the related rates problem, they'll replace the x. They'll replace the x with like a, I don't know, like a 3 meters. Okay, this is incorrect. X here is definitely a variable. When we say we want the rate at which the ladder is slipping down when x is 3 meters, that doesn't mean x is always 3 meters. It just means that x and y are changing, and how they're changing is related to one another. But at the instant when x is 3 meters, we want to know how fast y is changing. Okay, so please don't do this. This is not a constant value. It's a variable. So let's make it a variable. Okay, so how are we going to solve this problem? Well, related rates problem always start out the same way. First thing is write an equation. Usually it's geometric or trigonometric that relates the variables. In this case, we have variables x and y. They are inside a right triangle, and Pythagoras' theorem relates the variables. Okay, so I can say x squared plus y squared equals 5 squared. Okay, that's the relationship between x, y, and the hypotenuse. Now, the next thing that you want to do is take the derivative with respect to time of both sides. And usually for related rates problems, it's always going to be this way. Okay, so we're always going to be wanting to take the derivative with respect to time. I'm going to move this down a bit. Okay, now as you take the derivative with respect to time, so what we're doing is implicit differentiation, you want to keep in mind that both x and y are functions of time, meaning as time passes, x and y depend on how much time passes. And because of that, you have to apply chain rule, and you have to do that carefully. Okay, so on the right side, I think it's pretty straightforward. That's just going to be 0 because the derivative of a constant with respect to any variable is 0. But here you got to be careful. So when you take the derivative of x squared, the derivative of x squared with respect to x is just 2x. But you're not taking the derivative with respect to x, you're taking the derivative with respect to time. So here, what you want to do is apply chain rule to the outside function. Outside function is a power function. Bring the 2 down, subtract 1 from the exponent. But then you have to multiply by the derivative with respect to time of the inside function. The inside function is x, and x itself is a function of time. So this guy here is a function of time, and this guy is also a function of time. So here it's going to be dx by dt plus 2y dy by dt. Again, because y and x are both functions of time, and this is going to be common for related rate problems. Okay, one thing we can do here right away maybe is to divide both sides by 2. That'll just simplify the expression a little bit. Okay, and then this is a related rates. So here I just want to highlight you have 2 rates. Okay, so you have one rate and another rate, and these 2 rates are somehow related through this equation. Okay, and that's why these problems are called related rate problems. Okay, because basically what this equation is saying is that as the ladder slips, the rate at which the foot of the ladder slips away from the wall and the top of the ladder approaches the ground, those 2 rates are somehow related to one another. And that relationship is captured through this equation. Okay, now what we want is dy by dt when x is 3 meters. Okay, so we can substitute 3 for x, and then we can substitute yeah, 3 for x. But when we substitute 3 for x, we got to be careful. We have to be able to find y. To find y, we can make another triangle here. I'll just make it on the side. So when x is, oh, my triangle is in the opposite direction. So here's the triangle. When x is 3 meters, the ladder's length is always 5 meters. The y value is going to be 4 meters, and that's because this is a special right triangle. It's one of your Pythagorean triples, okay? So what I'm saying is, as soon as you know the value for x, you can calculate the value for y, because x and y actually are implicitly related to one another as well. Okay, so if you have the x value, you can easily find the y value. In this case, it happened to be a nice value as well. Okay, so I guess what I'm saying is we have the x value, we have the y value. What we're looking for is dy by dt, and we need some notion of what dx by dt is, but they tell us that. So they say, say the foot of the ladder slips when the feet are 3 meters from the wall, and they are moving at 10 meters per second. So here, it might not be immediately clear, but this value here, what they're giving you, is dx by dt. So what they're saying is you have this point B, and the point B is slipping away from the wall, and it's slipping away from the wall at a rate of 10 meters per second. Okay. Now, it's important to keep in mind that this value is positive. Sometimes the values will be negative. So like, for example, if they gave you a rate for y, we've defined y to be this length. If they said, oh, y is, the point A is slipping down at 10 meters per second, that would be a negative value because y's length is decreasing. Here, x length is, the length x is increasing. So this rate is going to be a positive rate. Okay, so we can say the following. We can say when x is 3 meters, y is 4 meters, and dx by dt is 10 meters per second. Okay, now this is kind of the general rate equation. Usually once you have a general rate equation, you have to evaluate it at a particular instant. We're doing it at the instant when the ladder is 3 meters. The feet of the ladder are 3 meters from the wall. So when we evaluate at this particular instant, we get 3 times 10 plus 4 times dy by dt. This all equals 0. Now, if you subtract 30 from both sides and divide by 4, you're going to get dy by dt is negative 30 divided by 4. It's the same as negative 15 divided by 2. Okay, now because this is a physical quantity, it's a rate, you have to express the units here. You always want to write down the units of your final answer. In this case, the ladder is in units of meters. Okay, so they told us here this is 5 meters. And then also they give us a rate, and the rate is in units of meters per second. Okay, so if we go down here, this is going to be units of meters, length, and then divided by units of time, which in this case is, seconds. So we have meters per seconds. Okay, you might want to write this as a decimal, so maybe like that. Now, notice something here. Notice that the rate is negative, and that makes sense because if we go back to our image, the length y here is decreasing. Okay, so it makes sense that that rate should be negative. And so the final thing we can do maybe is just write down a concluding statement. Therefore, we can say, what's the question asking? The question's asking, at what speed is the top of the ladder moving down? Okay, so we can say, therefore, the ladder's top is moving down at a rate of 7.5 meters per second. In this case, I've chosen to omit the negative sign. The reason I've chosen to omit the negative sign is because I'm specifying that it's moving down. Okay, so if you're specifying the direction, you can kind of leave off the sign. Okay, but the sign is very important and tells you the direction in which some quantity is changing. Okay, so that's important to keep in mind. Okay, so that was the first example. We're going to do another one. These related rate problems are tricky. Okay, so it's nice to see a couple different examples.